Okay, so cloud recording via Clark is up and going. Let me, why did this ribbon go there? Put this to the side. There we are. Let me test out my sketch pad, my digital sketch pad. Select blue, little X marks the spot. There we go. So that's working. All right. So why don't we get started? And so let's see, just brain hiccup. Oh yes, yeah. So today, the purpose of today is to finish up hopefully the material that we started on computer networking, and to as far as we can get through that, to give you a background that will be important when we pivot to connecting the embedded boards, the Arduino, and then eventually the Raspberry Pi to the internet. If we do not finish today, we will just finish up the balance of it on, I guess, a week from today, since Tuesday is the exam administration. So before we begin, some administrative bits. The reading by next week to review all of the material up to, well, Tuesday's class. And I have some resources for computer networking with the prefix net : for you to support all the material that we're going over for computer networking. I tried really hard to keep the costs for this course down as far as the textbooks that you would be needing. And so I did not require you to purchase the computer networking textbook, which can be very expensive since the focus of the course is not computer networking. That being the case, this smattering worldwide tour of various concepts in computer networking cannot do justice to a full semester of computer networking, but it is enough material to give you sufficient background for those aspects of computer networking that we'll be needing for this course. So if you have taken computer networking already, this will be fairly mundane for you. If you have not taken computer networking, this will be new and interesting to you. Project number 4, this is the old administrative slide, is already been passed in, so I won't talk about that. But written exam number 1 will be this Tuesday, the 1st of March, administered at 12 noon. And we will spend that class period going over the questions for the exam. It will be a 24-hour take-home exam format. It should take you about 1 class period. That's an hour and 15 minutes, plus or minus, depending on preparation. But the idea is for you to choose your own time and venue to set the exam when you feel you can be most productive. So it will be due via Moodle electronically at 12 noon sharp. And it will accompany, or will be accompanied by an honesty statement that you will be required to sign. I will not accept your exam and will not score your exam without the signed honesty statement. Okay, any questions about any of this? No questions? Okay, and hopefully I have it set so that you can unmute if you need to. I still know WebEx a lot better than Zoom. And so shameless plug, there's a whole semester of computer networking I have on a playlist for networking. I taught networking at my previous institution, among other stuff in machine learning. All right, so why don't we continue? No questions? No, all right. Let's see. All right, so why don't we get started? So when we last left off, we talked about the internet protocol stack, and we talked about the components that collectively comprise this thing we call the internet. And from a software engineering perspective, to manage this complexity, it's divided, the major categories of behavior, if you will, are divided up into so-called layers. And these layers pertain to various aspects of protocols that interoperate with one another to perform certain functions. And so at the top, we have your application. And this is where you typically come into contact with the internet. That would be, for example, your web browser or your instant messaging software, your email software, and so forth. And at the application layer, we refer to, or in networking, we refer to the unit of data as a so-called message. And so at each layer in this 5-layer stack, and the 5 layers are at the edges of the network at the host, because the goal with the design of the internet is to keep all of the complexity at the edges, at the boundaries, at the exterior of the network, and to keep the core very simple because you can make it really, really fast. And so at each layer, they traffic in certain types of information that have meaning for those particular layers in the 5-layer stack. For example, in the transport layer, it is responsible for sharing your single network card connection to the internet among all of the applications that are running on your machine that might enterprise to inject data into the network or to receive data from the network. And so for this, there needs to be information, namely the port number, and that's responsible for identifying the process, and more correctly, the socket that is associated with a particular flow of information. And this transport layer talks to the network layer, and this network layer's responsibility is to usher these units of data, these packets, across the network from one network card to another network card. And so included in that important information that's meaningful to the network layer is a so-called IP or Internet Protocol address. And you can think of it as a network-wide unique identifier that is used by the routing infrastructure to determine out which port this particular datagram, as it's called, should be forwarded. And then below the network layer, we have the link layer. And the link layer deals with the transfer of these units of data or packet between devices or machines or entities on the network that are so-called directly connected. And this direct connection could be through guided media, such as networking cable, twisted pair copper wire, coaxial cable, and we saw an example of coaxial cable, or in the airwaves, it would be anything that's reachable for that electromagnetic signal energy in some radius of communication. And so for the link layer, we call this unit of data a frame, and that piece of information that is meaningful to the link layer is link layer header, specifically the so-called MAC address, which we haven't talked about yet. And so this MAC address is unique, doesn't have to be unique globally. It just has to be unique on the local area network. And we'll talk a little bit more about that when we get to the MAC address or the link layer information. And so then we also have other components aside from those edge devices. And those other components typically are associated with the so-called network core. And these network core devices are responsible for ushering these units of data, these packets, from some source and endpoint in your communication to a destination endpoint in your communication. And so the first component, which we won't talk about at this juncture, is a so-called switch. And I'm still getting used to this again. And a switch, also called a layer 2 device, is also called a layer 2 device because it deals with information pertaining to the first 2 layers of the 5-layer stack, where we number them layer 1 at the bottom and layer 5 at the top. And the link layer pertains to your local area network, these islands of connectivity, these devices that are directly connected to one another without the need to store and forward packets. And so what this link layer does is eliminate so-called collisions. And so it means that 2 devices or 2 pairs of devices that are directly connected can concurrently, 2 or more, can concurrently exchange data without corrupting one another's signal information in that physical medium. And this other device, the router, is a so-called layer 3 device. So it deals with the physical, the link layer, sometimes called data link layer, and the network layer. And it's responsible for storing and forwarding these packets from one set of directly connected devices to another set of directly connected devices. So as such, in typical network setup, you're going to have a router. So I'll draw a router up above, and you're going to have some network. I'll just draw it as a cloud. And this router is going to maintain a connection or interface so it can talk to devices on one set of directly connected devices. And then it's going to maintain a connection to another network to another set of directly connected devices. And so you could alternatively, if you wanted to draw it that way, imagine these clouds here overlapped just in one place, and that place where they overlap is the router. And so this router is going to accept packets from one network because it's directly connected to those devices, and it's going to examine this header information that's meaningful, the IP address, and depending on the values of that IP address, it might forward it out one output port, let's label that port 1, or another output port, let's label that port 2. And so if you imagine then all of these sets of routers or a number of sets of routers connecting together a bunch of networks, in aggregate, the storing and forwarding of your packet from one network to the next network to the next network to the next network results in you being able to send a datagram, for example, from a Netflix server instance, say in a cloud, a data center, to your machine where you watch, your Netflix stream for some movie or some other such content. Any questions about this? Does that make sense? Okay, so I'm going to be like, you're going to see my eyes kind of change directions all over the place because I have a bunch of stuff going on here, as well as looking at who's unmuting. So if you have questions. All right, so why don't we continue on? We talked about the transport layer, and the transport layer, as we see, it interfaces directly with the application layer. And so the application layer uses the services of the transport layer, and through this construct we call a socket, it presents the illusion to the application above that it has a direct connection to an application on the other endpoint on the other side of this communication across the internet. And so it's really important when you create or design your network applications to be aware of the different levels of service available or made available to applications by the transport layer. And one is the so-called reliable service, TCP, which stands for Transmission Control Protocol. And one is the unreliable service, UDP, or the Unreliable Datagram Protocol. And so TCP, that reliability, means a number of specific things. At the end of the day, it means that your data arrives at its destination, and there's a guarantee for this, in the same way that you sent it. And so if you send a particular sequence of bits, 1010, at the destination endpoint across the internet in your communication, it's going to be received as 1010. So it will not be corrupted, and it will also arrive in the order in which you sent it. And that reliability comes at a cost. It comes at a cost of a number of resources, including buffer space, including computational resources, and that ultimately results in a slowdown relative to the available bandwidth you have in the connection between the source and the destination endpoint. Now, UDP doesn't have any of those reliability mechanisms, and because of this, UDP is much, much faster. But the bad news is that it does not give you any of those guarantees. And so the reason why you should care about the underlying transport layer services that are used by the application that you're implementing is this can make or break the performance of what it is you're enterprising to do. And so it's really important when you're designing an application to think about whether reliability is a necessary requirement for what you're trying to implement, or if your application can tolerate some errors. Now, UDP doesn't mean that, say, half of your messages are going to go missing or get corrupted, but you still need to think about whether or not your application can tolerate corruption. And so if you are doing something in banking, of course, it needs to be reliable, because if you have a bit error in your communication, something like transfer $100 could be transfer $2,000, and you wouldn't want that to happen. Okay. Any questions? No questions? No? All right. So the socket construct is an API, and in object-oriented languages, it's an object, and the methods made available by that object instance implement the various commands or behaviors, if you will, that this transport layer service can engage in. If it's language implemented in a language where it's not object-oriented, or procedural language, for example, it's typically a set of function calls that each implement the various behaviors that are made available by this programmatic interface. And so the socket is that construct that straddles the scene between the application layer above and the transport layer below, and that's how applications are able to inject data into the network, send, or to receive data from the network on the other side. Any questions? No? All right. All right, so why don't we get started? Let's continue on with our discussion of sockets. And one of the important things in the internet that was not an original consideration is security. It was assumed that everything would be warm, fuzzy, and friendly, and that's certainly not the case. And in particular, as more and more financial and other sensitive types of applications make their way to the internet, securing your communication has become increasingly important. Cyber criminals, or criminals rather, believe in continuing education, and so they are absolutely ramping up on how to apply certain exploits in order to profit, if you will, through getting into communications. And so TCP and UDP, by their design, do not implement encryption, the scrambling of data, so that it cannot be understood by observers. And when we look at Wireshark in the afternoon session, we're going to see just how easy it is to view or intercept data that's available on a shared network. And so in an application like email, you enter in your name and password, or banking applications, stock applications, or even just logging into your student information system. Now, passwords certainly shouldn't be sent in so-called clear text, meaning not scrambled. The casual observer can intercept it over the network and then make use of it subsequently. And so there's a version of a socket that is secure, so-called secure sockets layer, or SSL. And what SSL does, it takes this information, let me go back a few slides, that is sent as a message by the application, and it implements encryption inside of the socket runtime. And then once it does the send, it's now sending encrypted data, but it's not always completely encrypted, because there's certain information that cannot be encrypted, namely the port number and the IP address. So there's still some information, but the message data is what is encrypted by this socket. And the converse operation happens when data comes from the network at the destination endpoint. It decrypts that data. Now, certainly, this is not a network security course. Dr. Femi is teaching the security course, so I will not cover mechanisms for how SSL works. I'm happy to point you in the right direction if you have questions about it. And so what this encryption afforded by SSL gives you is so-called data integrity. That means that you can guarantee that those who aren't, to a certain degree, guarantee that those who aren't entitled to view certain data will not view that data. But having your data encrypted is not enough. You also need to do so-called endpoint authentication. Take, for example, a banking application. When you are connecting your browser to your bank, say chase.com or whatever, you really want to have a semblance of assurance as to, yes, this really is my bank that I'm connecting to. And so this endpoint authentication is a mechanism to give very good guarantees of the identity of the thing that you're connecting to. Because you could initiate a connection to a website that you think is your bank and make an encrypted connection, but that's really not your bank that you're talking to. And there are a whole host of approaches and mechanisms for doing that that are covered in a typical network security type of course over a semester. Okay. Any questions about this? No questions? All right. And so typically, when you look up SSL, it's a separate library, and this library has API calls that will do things like authentication, check certificates, do encryption in various ways. Okay. So let's take a look at HTTP, Hypertext Transport Protocol, which is the most popular protocol driving web type applications. And there are many categories of applications that so-called piggyback on top of HTTP. And so a web page is nothing more than a structured document. And in this special document, it has fields, and each one of the items in this document, it could be a list, it could be a field, it could be a heading, it could be a title, it could be a paragraph block, so forth, or an image. Each one of these is a so-called web object. And so this structured document we call a web page is nothing more than a structured document, and your HTML code is nothing more than a block structured layout language that describes the beginning and end of a block and the content, namely the set of objects that are inside of each block. And so in rich web pages, and I remember When the graphical web first came out, it was just static. It didn't have dynamic or executable content. But in a rich web page, you can have all sorts of stuff like video, programmatic information, server backend calls, all sorts of amazing things. But in this web page, it starts out as a base level page, your index.html file, if it's PHP, do other things. And this base HTML file needs to be identified. And so this identification system, a so-called Uniform Resource Locator, or URL, is nothing more than a distributed file system schema. And so let's imagine we have some machine, let's say it's our server, and the server has an internet name called a domain name or its host name. Now, this domain name is nothing more than a nicety for human consumption because all the internet needs, the 5-layer stack really needs, is this IP address we talked about, which is relevant or meaningful to the network layer. So the server has attached to it a file system. And in that file system, maybe you're going to have your index. Oops, let me see if I can write that small index.html file. You might have an image, img1. .jpg, for example, a JPEG file. And so now you, the client, when you load a web page, that web page might have some text, and maybe it's going to have a background of a certain color. And then it might also have an image that it's going to display in that region for a background that's a certain color. So first thing you need to do is identify this document. That might be your index.html file, your top level document, but you need to identify all of the objects that you need to load in order to draw this particular structured document on your web page or in your browser. And so this object needs to be referred to, and how you refer to it is by two things. For one, first you need to identify what that server is, where it can find that particular object, i.e. that image file. And so that server has a name, and that name is a host name. Now, in this particular example, it's www.someschool.edu, but there's a mapping system called Domain Name Services, or DNS, that maps from this name that's textual, that makes sense, or it's easy to remember for human consumption, to this IP address. And so you're going to have one of two things, either your IP address, and that might be one of those numbers of the form 119, and I'm just making this up, 128.34.7, for example, or a synonym for this IP address might be someschool.edu. And so once you've identified the machine or the host where this object is found, then you need to say, okay, well, where on the disk is it? Now, maybe it's in a folder someplace. You identify that path name, that folder, and then ultimately identify the particular image file, if this were an image. And so each object that comprises all of the pieces of your structured document for your web page is referred to or addressable or identifiable or located by a so-called Uniform Resource Locator, or URL. Any questions about this? No? All right. So we have this top level document, and that document will either have directives to say things like make the background purple, place some text, or it will load images or videos or other content. And so the first thing that happens with this hypertext transport protocol is your browser, when you say www.someschool.edu and hit enter, your browser is doing a bunch of things. Now, as a convenience for you, when you say someschool.edu, your browser is inserting port 80 on the end of that for you. And we'll actually see that in Wireshark in the afternoon session. And of course, the HTTP that you type in your browser is the protocol. And so when you type in HTTP, you're telling your browser, use the hypertext transfer application protocol, use this domain name, and your browser, as a convenience for you, looks up the IP address for someschool.edu. And then the browser inserts this :80 on your behalf, but you could certainly type :80 directly. Now, does that work for every website? No, it doesn't. A lot of universities and other larger organizations use a so-called content management system, management system, or CMS. And this is a platform that makes it easy to edit web pages, to post new content. And so oftentimes when you have these CMS systems, they'll use a different port number from the default port number for the internet. So it might be like port 8080 is a popular one that they use for these CMSs. But nonetheless, your browser is still inserting a lot of stuff for you as a convenience. But underneath the cover, from the protocol standpoint, you have a host name, you have a path name, a port number, and then you also have a path, and then the object itself that's on the file system for that remote machine. And so the first thing that happens, and I remember when the graphical web and web-based applications first came out in the mid to late 90s, at that time, when you had a distributed application like email, you had to install software on the local machine, just like how you might install MATLAB or you might install Microsoft Word. Now, if you wanted to issue a patch or an update, you had to convince those millions of users to install new software on their system, which is really, really hard thing to do. And so what these web-based applications did, and I remember this, is that if you want to upgrade the software, the only thing you need to do is install your updates on the server. And just by nature of how HTTP works, every time someone fetches that web page in the future, they automatically get the latest updated version. And so it exploded in its popularity, got very, very popular because it solved the practical problem, and that was not having to recall somehow all these machines and client machines and convincing people to update their software, which was by DVD at the time and not by downloading. But that being the case, this hypertext transfer protocol also enabled the ability to have multiple types of user interfaces to fit the particular client type that someone was using. And so if someone had a PC, well, you have a lot more screen real estate, and you could structure your web page for optimal viewing on a PC, and then the same website could serve up this web application in a different form factor to fit something that was a smaller mobile device that had a smaller screen. And so in this example, we have a PC running, say, Firefox browser, and you have, say, an iPhone device running Safari. And as long as you implement this HTTP standard, different clients with different browsers will operate with the same server. And as we said before, Apache is the predominant, most popular web browser in the marketplace. And so we have our PC running Firefox. It does an HTTP request, which is to fetch content, be they structured document descriptions, HTML files, or the objects inside, and then it gets back a response, namely the result of the server performing work, which is to look up on its hard drive the content identified by the URL in the request. It pulls it into memory and sends it back across the wire to the requesting browser. And so if you have another device, such as your cell phone, your smartphone, it does an HTTP request and gets back the response catered to its form factor, namely the screen real estate. Any questions about this? That makes sense? No? All right. And so HTTP, if we look at what a document is, and this is going back to our discussion on what we're just talking about in terms of the requirements of the application, if the structured document description, your HTML file, has corruption, or things are out of order, or things are missing, it's going to look like just hieroglyphics, right? It's just going to be corrupted, and you're not going to really be able to read the web page, or maybe not even be able to draw anything at the browser side. And so you need reliability for web page content. And HTTP, for this reason, uses TCP, the Reliable Transport Service. And so with TCP, your client initiates the connection through a socket, And when you instantiate a socket, and it might be different depending on the implementation in the language that you're using for your client software. In some, you instantiate an object and it initiates the connection for you when you instantiate in its constructor. In others, you explicitly have to call API calls in order to create that socket. And so once this initiation happens for the connection, this is like that first round trip we talked about with this communication between Alice and Bob. You're establishing the resources needed in order to engage in this reliable transport. And so that means that you are asking, you being the client TCP runtime, do you, the server, have the buffer space, have the computation ability, have the timers available in order to keep up your end of the bargain, so to speak, in what it means to do reliable transport services. And so once the server, as part of this initiation of a request, once the server responds back a yes, it means that the client can expect the server to be able to engage in the server's responsibilities for this reliable communication. So then subsequently, you have the HTTP protocol messages, and those are the requests to fetch content from the file system on the server. And this initiation is done under the covers for you. If you read in the literature for TCP, it's called a three-way handshake, and we won't talk about that. But you don't have to implement this initiation. It's done for you by the TCP runtime. But what your application does have to do is look at the status code of this initiation that says either the server has the resources, it can engage, or the server does not have the resources, it cannot engage. And how you deal with this potential exceptional condition or failure mode is entirely up to you. You could retry, or you could present to the user, sorry, we could not make a connection. And HTTP is a so-called stateless protocol, and that statelessness is really, really important. When I was working in industry at Sun Microsystems, among other places, Sun made an absolute fortune off of stateless servers. And a stateless server is one that does not record any state or past history about where the connection is. And an example of that is, suppose that you're searching for a database. A stateful connection is one that knows where you left off in the database. A stateless connection is one that maintains none of that information. And so when you maintain state in a connection, that state requires a lot of resources. And as you scale the number of clients that can interact with your system, you reach or exhaust your resources very, very quickly. And so stateless servers tend to be much more highly scalable. And HTTP is a stateless protocol. And because there's no state maintained by the endpoints for the connection, it's up to the client to furnish what specifically that starting point is for the particular request that it has. And so the cost of maintaining where you left off is charged to the client and not to the server. And that's how you get stateless server applications to scale so much better. Okay, so this is an example of a request that an HTTP client or browser would initiate to a web server, and it's in text, it's clear text, and it's done in clear text because, for one, it makes it easier to debug, and for two, it made it really easy to implement. And so it consists of three main components. One is the request, what it is the client is asking the server to do. So here's my request, that's the first line. And then it has the header lines here. And the header lines you can think of as meta information that describe important aspects of this communication that the client is engaging in with the server. And then after that, you could have your some data or payload, but typically that's not done. And I'll talk about that in a slide or two. And you'll notice here, each one of these lines is specifically delimited with a particular character that has to be a carriage return, \R, followed by a new line. Now, back in the early days, when you had teletypes, and I remember when I was a little kid, like 5 years old, these machines, you had the output not on a screen, it was on a special printer. And there was a command called carriage return, and carriage return meant if you had, it was sort of a spool that was round like that, and then you have this print head, and I'm not going to do the artwork justice. and this thing would go to the left or to the right, and then it would strike a character on whatever piece of paper on a spool happened to be passing by it. And so carriage return meant take this carriage and return it all the way to the left-hand side, assuming Western language where characters go from left to right. And then the line feed meant to advance the drum one line of text so that you could type on the next line. And so that those roots of computing have sort of persisted in some of the protocol design. And we see that in an HTTP request, where each of the command lines in an HTTP request is delimited. It ends here with a carriage return line feed character sequence. And so that being the case, our request line is the specific command or behavior that the client is requesting that the server engage in. And so the popular one, or in this example, I should say, it's a GET request. And this GET request, the client is telling the server, I want you to fetch a particular piece of content and send it back to me. And so you have your keyword, which is the command that the client requests of the server. And then you have the name of the object. It could be an HTML file, it could be a GIF file, it could be all sorts of stuff. And then the next field talks about the protocol number. And this is HTTP / followed by the protocol number 10, 11, and there are other versions. And what this protocol number is telling the server, this is the set of messages and behaviors that are understood by the client who's requesting this. And so some servers will be backwards compatible with older protocol versions, some servers will not. Now, if a server does not support that protocol, the server will say, I'm sorry, I can't engage in this conversation with you because I don't understand that version of the protocol. And so then when we look at the header lines control all sorts of useful things. And we'll point out just a handful of them, not all of them. And so this host specification, all of the entries in a header line is of the form some name or variable is equal to some value. Now, it doesn't use an equal sign, it uses a colon. So here, it's the host variable is equal to www.net.cs.umass.edu, and then we delimit that line. Here, we say the user agent, that's the variable name, and its value is Firefox version 3.6.10. And so these name value pairs control a lot of things or carry a lot of useful information about this connection. And so for some servers, you engage in different behaviors based on what particular browser software that you're using. Are you using Internet Explorer? Are you using Safari? Are you using Firefox? And that can include a whole host of things ranging from how you arrange the structured document to whether or not you can support that particular browser. I know some applications, when you log in, it'll say, just by logging into that website with your browser, it'll say, sorry, we don't support that browser. You're going to need either Firefox or Internet Explorer if you want to use this banking application. And so it's the user agent name value pair that is used server side to garner that information. Another important one is the accept language. And that accept language can exist in a number of standard codes, the values, and this is used for multilingual websites. Now, there's some websites, particularly overseas, when you connect to them, they will automatically show you the French website or the German website, Spanish website, or English website, British English versus American English, and so forth. And so oftentimes what they do underneath the covers on the server is that when this request comes in, server looks at the accept language header line entry, and if it's a British English, it's going to get that website content from a different directory that has all the text using British English or using French and so forth. And then this last one, I'll just talk about two of them. One is the connection variable. Now, this connection variable talks about persistent connections, and there are different ways you can fetch content but from a web server by a browser. One is so-called persistent connection, and that's where you keep the same connection open and you just request different content along the same connection. And the other is non-persistent connections. That's where you open up a new connection for each piece of each object that you're trying to fetch from the browser, from the server going back to the browser. And then this keep alive is typically a unit of seconds that tells the system, the server, how long to keep this connection open. And so typically connection and keep alive are go hand in hand. You're going to keep the persistent connection, which can result in performance improvements, and how long you're going to keep this connection open. Okay, any questions? That makes sense? Okay. And so this is just a generic schema for what the request message looks like in HTTP. You have the method, which is the behavior. You have the URL for the resource. You have the version of HTTP and a whole host of other header lines. And then optionally, you can have a body which can contain data. But in most modern web implementations, they don't use this with the client request because it's dangerous to upload code to a server or upload data or objects to a server from a client. Okay. And so there are different methods that you could use to upload, and uploading was typically in the earlier days the post method, and it was used in the beginning for doing web forms. And so the ability to fill out forms, maybe you're collecting someone's name and address, but this post method is not used very often because modern implementations typically have databases. And so how it works now for safety's sake is you want to get the data to the server, but you don't want the server to, install something or write something to its hard drive. And typically what they use is something called the URL get method. And what they do is they put a suffix, a bunch of other text on the end of the URL. And those things on the end of the URL are in the form of name value pairs. And that's on the end of the URL. So for example, www.somesite.com, okay? And what you're fetching is what looks like something that's in a directory, but that's really a method name that describes an operation you want the system to perform. And then you also have your name value pair. So here's a name or a set of variables. Name is equal to a value. And then they separate the different variable names with ampersands. And so this would be your method. In encoding, you're pretending your directory, you're using that directory on the end of the URL as a method on the server side. And then you have name value pairs, which are the parameters to that method that are as specified as suffixes. So you can imagine somewhere on a server, you have a method, in this case called animal search, and you have some parameters, monkeys, for example, etc. Right? And so one example that you're using today, when you go to youtube.com and you want to watch a video, your URL has the following structure. You have the host name, youtube.com, and that translates to ultimately a server instance that's running in the data center. And then watch is your method, and then your name, V, stands for video, equals, and then you have a unique identifier hash code for your video, right? And that's in the direct example of this URL get method. And typically what happens, you have your client and you have your server. And the server is a process that's running on some machine in a data center. And as a machine, you have more than one process running on it. And you have a set of co-processes. And one of these co-processes might be a database engine. And that database engine talks to a storage array to get that content that is parsed by the server. And so this is a lot safer than the server implementing the post method, where the server would write directly to the file system that opens you up to a certain category of injection attacks for viruses to compromise your organization. It makes it a lot easier because this is read only, not write, and it takes that read and parsed information and it sends it to the code process that then goes ahead and does something, interacts with the file system, and things like that. Okay. Any questions about this? Does that make sense? Yeah. Okay. So the difference between HTTP 1.0, if you look up the RFCs, the specifications for these various versions of HTTP, you'll see all the different methods they implement and what the fields mean and what the behaviors are for the server's responsibility for engaging in or supporting these particular versions of the protocol. And so HTTP 1.0 was, of course, the first version. And then with subsequent versions, they added different methods. Some of them they use, some of them they don't use. And if we look at HTTP 1.0, you can see the post method to send data from the client to the file system of the server, and the delete method. Those can be very, very dangerous. So you can imagine someone hacking into a system and issuing a delete in their post. And so now they've injected their own server-side include or executable scripts onto the server to do all sorts of things. And so for many deployments for web server, they tend not to use the post and delete because that's inherently dangerous. And they have other means that just scrape information from the get command from those suffixes that are on the end of the URLs. Okay. And this is a response message. And the response message is what's returned from the server back to the client in the communication. So your browser gets this. And it has a status line, that first line, and it just tells you what the server's result was of the work that the client requested for it to do. Now, that result could be, I couldn't find what you're asking for. It could be a whole host of other things, and there are a standard set of codes, response codes, that are meaningful in HTTP in these specifications. And so in the status line, the first thing you'll see is the protocol version from the server, a code number representing the status, and then a text description of what that code number is. The server then also includes some header lines to talk about various things like the timeout for the keep alive, whether the connection is going to be persistent, in addition to the server software version, in this case, Apache 2.0.52, and the operating system that it's running. Now, certainly for a security standpoint, the server does not have to return all of this information in the header lines, because if somebody is very conversant, for example, on exploits for the particular operating system in which Apache 2.0 family is installed, that might be something an organization standing up the server might not be willing to return back to the outside world for anyone who connects with the browser. Okay, and so these are the status codes. And if you ever go to a website and just type in, for example, disney.com/nothing.html, it's going to return back a 404 not found web page. And it might have some, cute animation on it. But these are the status codes, some examples of status codes that are responses that a server can return. Now, certainly, excuse me, certainly this OK status code means that the server was able to successfully perform that work. And you can expect that in this data field, it's going to contain either the bytecode if it's some object like an image file, or the HTML if it's something like a web page, a structured document description. Okay, and so let's take a look at a particular socket example. And again, we said a socket is that software construct that straddles the seam between the transport layer and the application layer. And of course, the application layer is completely controlled by you, the application developer. And for some operating systems, you can tinker with details of the transport layer. For most consumer grade user operating systems like your Windows products and Mac OS, they don't really like you to go into the operating system kernel and tinker with things. The Linux is, you can always go in and tinker with it. Now, why would someone want to tinker with transport layer? Maybe you are implementing services in a data center, and you want to, based on the type of workload that these web servers are getting, you want to alter the way the data flows between the source destination endpoints. But nonetheless, the socket is that API, and it offers in IP version 4 two different flavors of communication. We mentioned before the reliable service, which is TCP, and the unreliable service, which is UDP. Now, TCP is a so-called connection-oriented transport, meaning that once you establish the connection, with this open connection, you then just send your bytes through this socket mechanism. UDP has no connection, And a result of that means that every time you send a datagram to the destination endpoint, and for the server, you send back that response, you have to address specifically on each datagram to whom it's going to go and what port number it's going to use. And so in the example in the Carosa-Ross textbook that we're kind of lifting all of this material from, there's code, and I will kind of go over it at a high level, where you're going to type in, and it's written in Python. You're going to type in a line of text at the command line when you run this program, and the client is going to send this data to the server. And if we were in person, we would actually have you use Wireshark to intercept these packets, but this can't do that over the wide area very easily. So the server is going to receive this text, and the work it's going to do is to capitalize this text sent by the client, and then the server sends back this result of capitalization back to the client, and the client gets it and displays it locally on the screen. And so UDP, as we said, it has no connection. And when you establish a connection, that connection establishment that we talked about for TCP is the querying of the server as to establishing the resources needed to engage in its responsibility for reliable transport. And so because there's no handshaking, no establishment of resources for UDP communication, you have to attach an IP address and a port number for every packet. But with TCP, once the server answers, yes, I'm able to communicate reliably, you don't have to send that information on every single datagram. You just write into the socket, and the runtime for TCP handles the rest for you. Okay. And so in UDP, the generic schema, you can think of this as a protocol diagram that relates something that looks like Python code to all of the steps in the API used to communicate in using this unreliable service. And so the first thing you need when you create the socket is you're going to need that port number, because your port number is how the runtime on your endpoint, the client, identifies which application to source this particular datagram or which application to send this incoming datagram to. And so you establish a port and you create the socket. Now, certainly if you're using an object-oriented system, you just instantiate the object. But in this case, it explains from a procedural standpoint, because underneath the covers, the object is doing each one of these steps. And so you start out and you specify this AF-INET refers to Internet IP protocol. And then you have to specify what type of service. Socket dgram is a constant that represents the fact that it's unreliable service, datagram. When we do the TCP example, you'll see that this socket type is going to be different. It's going to be a so-called stream socket and not a datagram socket. And so you have to tell the socket API what type of socket you're going to establish. And you also have to tell it this is the IP address that you've adopted. Now, that can be done a host of ways. It can be done ephemerally, or it can be done explicitly. And I can talk about that in another sitting. Okay, so now, of course, you have your server running and you create your client, and the socket types have to match. The server knows that it has a datagram socket, and the client also knows that it has a datagram socket. You can't say, I'm going to create an unreliable socket, UDP, and talk to a server that understands TCP, because the two protocols are different. They're different protocols within the same transport layer. And when we talked about a server from before, we said a server has to be always on and running. So you'll notice in this flow of protocol diagram, here we have the server on the left, your left, and we have the client on the right. And as we go down the screen, time increases. So the first thing that happens, the socket on the server is created, the socket on the client is created. So then the client creates a datagram, and it stamps that datagram with two pieces of information, with the server's IP address and the server's port number. So that means the client needs to know the IP address and the port number for the server. Now, how you get it to the client is entirely up to your implementation. You could hard code it, or you could get it to the client in some fashion. That's not specified here. Now, when the client creates this datagram, for this UDP socket or unreliable transport layer. It then stamps it, and then it goes ahead and sends it. Now that it sends it, the infrastructure that we talked about, the routers and the switches, have everything they need in order to usher this datagram from the source endpoint, the client, to the destination endpoint, which is the server. So now the server, on its side, it's created this UDP socket, and it goes ahead and does a read operation on its UDP socket, and it either gets data or it doesn't get data. Programmatically, there are different ways of doing this. You can have a so-called blocking call and poll, but in modern implementations, you have something called asynchronous I/O. You have the system wake you up, the server, whenever that there's information inbound on the network card into the buffers for your transport runtime. And so the server reads its socket, and if it has data, it takes this data, gets it into its memory, and then the part that's missing here is performing work, right? And that work would be to capitalize, it could be to look something up in a database, what have you. And as a result of that work, it gets a result, and then it sends that back across the wire through its UDP socket. Now, of course, when it got that message, that socket was also stamped with the IP address and port number of the client that sent this information. The client needed the server's information because it needs to know who is the destination, both the network card, the IP address, and the process at that network card. But the client knows its own IP address and knows its own port number. So the client furnishes that, but it still has to know what the destination is. Because in the same way, when you're mailing something, you know what your return address is. You know your name and you know the house where you live. And so you know this information, but you need to know who you're going to address this to. So when the server is ready to send back the response, along with the request from the client on this UDP packet, it extracts the client's IP address and it extracts the process's port number, and then it goes ahead and sends down the wire the response to the client, and it knows how to address it because it pulled that information from the incoming communication that it got, the request from the client. Okay, any questions about this? No questions? Make sense? All right. So now, once the client sends, from its perspective, it goes ahead and tries to read from its socket. You send something and then you read. It's almost like you mail a letter and then you wait by your mailbox for a letter to come back to you. And so when the client reads from its socket, again, whether it's a blocking call or asynchronous I/O, it either gets a message or doesn't. Once it gets a message, it extracts the response and then it closes its socket, and the request response cycle has ended. Okay. So in Python, for UDP, you'd implement it in the following way. So the first thing you're going to do is pull in the libraries. Now, if you were in something like C++ or Sketch on the Arduino, you're going to include a header file in your #sign include block that's going to pull in the definitions for the socket API for Sketch language for the Arduino. The server, the client rather, is also going to obtain somehow the server name and the server's port number. And that's needed because it's going to stamp, as we said before, each packet, because this is UDP, with the IP address and port number for the server. So the next thing that the client does, because this particular example is to capitalize something that's input at the keyboard, it's going to go to the keyboard and say, all right, well, type something in at the keyboard. That's this message that it gets, and it's just text. And it goes ahead then and takes this text and it sends it through its socket. And so it created the client socket. You notice it's IP version 4, and it's also a datagram socket. And the two versions of IP right now, IP version 4 and IP version 6, and no one really talks about IP version 6 in computer networking. It's still, we're sort of still transitioning large scale to IP version 6. But that being the case, once the client gets the data from the keyboard that you type in, it goes ahead and this messaging code is to convert from ASCII, which is platform and locale specific, to a wire format that you can send across the network. And then it goes ahead and it furnishes, and you'll notice this is really important, the server name, which is the host name. It could be a domain name, or it could be the IP address and the server's port number. And so this second parameter, which is a tuple, is how the client knows where to send, or what the client uses as to where to send this particular datagram. And so once the client does the send, it goes ahead and it reads the socket. So it does a client socket receive from. And for Python, when you receive data from the network card, you have to store it in a buffer someplace. And in Python API, you give it specification of the buffer size it uses to receive. So one question you might ask yourself, well, how do I know how big the buffer should be? Well, if you design the protocol, you choose the size of the buffer it's going to use to store this particular data that it's going to get from the socket. Now, certainly a socket, when you send a datagram, the average size these days is 4096 bytes. Certainly you could tune that, and fragmentation can happen. It can chop it up to smaller pieces depending on your network. But for a host and plain vanilla TCP/IP, the packet size is typically 4096 bytes. So that being the case, in the application, when you receive data, you have to furnish the size of the buffer, at least in Python in this API, that it's going to use to store this data, because it's read from the network card and from the transport runtime into the application's address space. So you have to store it somewhere and specify how much storage you're going to use. So then after that, it gets the address, and you notice here, when the client read from its socket, one of the pieces of information that it gets is the server address. And the reason for that is, if you are going to send a subsequent message, well, you need to know where you're going to send the next message if you're going to continue communication with that entity, that endpoint that just sent you this response. Okay, so then you, of course, take your message, you print it out, and then you close that client socket. All right, any questions about this? No? And this would be a lot nicer if we were in person and we could sniff this with Wireshark and you'd actually see this in action. All right, so let's take a look at the server side. So the server knows its IP address because it knows what machine it's on, and it also knows its port number, chooses a port number. Now, one of the things that you need after you create a socket on a server, well, here we have use IP version 4 and make it the unreliable service datagram socket. The server does this command called a bind. And what a bind is the association of that socket with a port number. And so if I draw the top two layers, we had the application layer as layer 5, and we have the transport layer as layer 4. And we said the socket straddles between the application layer and the transport layer. Now, when you bind and you give a port number, you're saying, okay, create the socket. So here it is. We just created the socket. Now we have that magic door between the application and the other endpoint on the other side of the internet. Now we need to identify this particular magic door. And when we say bind with this port number, we're saying, okay, call this door number 1200. So now, or 12,000, I should say, my mistake. So now, once you do this bind, when an incoming datagram flows into your platform, to your runtime, it knows if this thing is stamped with 1200, that it's going to send that to a particular application. Maybe it's your chat server, right? Now, you could have a chat server. You could have maybe a web server. Web server uses port 80. So for web server, it has a port, a socket associated with it, and that is stamped with an identifier, port number 80. So you can have incoming data on the same network card stamped with 1200, maybe the next one is stamped with 80, and then the next one is stamped again with 12,000. I keep saying 1200, 12,000. And that's how your runtime knows to which application to forward this datagram. And so this bind is a requirement for your server, and it's how your transport layer runtime associates one of these doorways of communication with a particular application. Okay, any questions about this? Does that make sense? Okay. I'm just sort of checking the time. Wow, a lot more time than I thought this would take. No worries. All right, so then the server, it's always on. It's associated itself with an IP address because it knows its network card for the machine it's running on. It has a port number. So then the server sits in a tight loop while true, and then it does a receive from. It's listening on that socket for an incoming connection. So once this receive from, which is a blocking call in this case, it returns, it has the message, and then also has the address, IP, and port number of the client that sent this message. It unpacks the message from this socket that it received. It goes ahead and performs some work, in this case, convert it to uppercase, and then it sends the response, the modified message, the capitalized message, back across the wire through the server socket, its socket, to the address associated with the client that it got this request from. Okay. And from the client standpoint, which we talked about before, it sees that message. And so what does the server do after sending back that response? It loops back and it listens for the next request and listens for the next one and listens for the next one. Now, in this case, the work is pretty simple. It's to convert it to uppercase, but you can imagine if what happens in here is a complex operation of consulting a database and doing some other more complex types of operations. Okay, any questions? No? No questions. All right. So when you program with TCP, the client has to contact the server, and therefore the server process has to be running, TCP being the reliable service. And when you contact the server, just by contacting it, this connection is established, and you don't have to stamp each communication with the IP address and the port number. This is done as a consequence of this establishment of the resources. And so you start out, and we only have 3 minutes left or so, with the server running on a host. The server starts out, creates its socket, it knows its IP address, and it chooses its port number. And in an object-oriented language, it's assumed that this bind happens, but you always do a bind with the server. You always have to say associate the socket with a port number in the transport layer runtime. So then it waits for incoming connection, it accepts the request, and when it accepts the request, you'll notice here another socket gets created, the so-called connection socket. And so there are two sockets involved with the reliable transport in TCP. There's the server socket, and that server socket is responsible for establishing resources. And once those resources are established, for each connection, you get what's called a connection socket. And it's through this connection socket that you send and receive. And inside of this connection socket is encoded the IP address and the port number of the client that you're going to communicate with, because this connection socket is unique to each client. And so here we have, say, client 1. We have, say, client 2. We have a single server. And when you establish a connection, you get back a connection socket. I'll just call it CS1. And now CS1 maintains a bidirectional pipe to the server. And it's through this connection socket that client C1 uses in its communication with the server, and the server uses with its communication back to the client. In similar fashion, client 2 establishes the connection, and as a result of connection establishment, it gets this connection socket, we'll call it CS2, and this is a bidirectional pipe to communicate with the server. And so the only purpose of this server socket is to listen for incoming connection establishment, to establish the resources, and underneath the covers, the instantiation of those resources for single connection is underlied by this connection socket that the client uses. The server has its own endpoint for the connection. Any questions about this? Make sense? Yeah? All right. So I'm going to finish up with this. So the server accepts the connection. That means it's established its resources, and those resource instances for this connection bidirectional between the server and the client is abstracted by the connection socket. So then the client comes along, creates a socket, and when that is established, the TCP connection setup, when it returns, if it's successful, that means the server has an instance of these resources abstracted by the connection socket, and the client can now use its client socket, as it's called, to communicate and bidirectionally with the server. And so now the client uses its side of the socket, its client socket, to send a request. The server then reads from the connection socket, not the server socket, but it reads from the connection socket, that abstraction of the bidirectional pipe with the client. So then it gets its information, its request from the client. Missing from this diagram is the work that's performed. The result of that work, it then writes back as a reply using the connection socket. And so once this reply is written, the server is going to close its connection socket. And underneath the covers, the runtime doesn't tear down the connection after the server closes, because it says, all right, there might be data that's being read. What closing the connection socket means is the server can no longer send new data on its side of the endpoint. And so the client gets back a response from the server, and then it closes its side of the connection, and the communication is done. Okay. Any questions? No questions? All right. So we're going to stop there. It's now 11:40, and that's time. This took a lot more time than I anticipated. So what we'll do is we'll pick back up at noon with Wireshark. I have to figure out how to do this. I practiced a little bit, so we'll see what happens. Maybe get to see some bits, and maybe we can just poke around the internet and use some other tools to show you some things about infrastructure. Okay. So I will see you then. Let me stop the cloud recording.